Wow, you know, you got to see this. Oh, maybe that's make that too. Where's the camera? Can we move the camera?
It's pointing here.
Yeah, it's easy to move the camera. Okay, so you're looking at our Belgian seismologist. Can I actually hold that?
Yes, we are.
So this is, this is just while we're getting ready here. Okay, are you ready for this? So
I'm not sure.
You're not.
I'm very busy.
Yeah, feels like I'm on a VR ride.
Okay, so can you see what does that look like?
Oh, that looks like a very nice seismometer.
Seismometer, and you did your PhD in electromagnetics, and you know about seismometer. We are impressed.
Picked up a few things.
Wow.
That's awesome. That's awesome. So this will be the topic of the next video.
Kevin will be making this in his next video.
Yeah, so there we have it.
Yes.
That's super cool.
The only thing kind of not so good with that is that it's sugar frosted flakes, which don't make the
Swamp shelter.
the good.
Come on,
the good
Cheerios
stuff.
is not better than
Cheerios, you like well a little bit.
it's all sugar.
As long as you don't have the multi-grain, you're good to go, right? But just sorry, that was a little bit of relief while we're.
I'm thinking
All right.
I like it.
How about that?
Oh, well, I'm looking forward to seeing the video version whenever that comes out and is shown to the world.
It's gonna happen.
Okay, on to more serious.
All right. How to follow that up? Gosh, I just have pull requests. So I just have two quick updates, and then anybody else who has quick updates, feel free to jump in. We just merged this morning a pull request from Dieter, which updates the versions code in SimPEG. And so what that does is if you include it in the end of a notebook or in the end of a script, it'll print what versions of like base software that you're using and also the version of SimPEG. So for example, if you're publishing research notebooks or something like that, and you want it to be clear what versions of things that you're using. Sorry, man, you're really lots of background noise. Thanks. Yeah, so that prints the versions of like matplotlib, numpy, scipy, pymatsolver, and discretize, as well as SimPEG. So if you're publishing research notebooks and like just want people to know what software you're using, you can add that at the end. So it used to be you would import the lowercase versions, and now it's uppercase because it's actually a class that you're calling. So have a look at the pull request notes. If you have any questions, feel free to ping on Slack, and Dieter, I can jump in and help. It should be a very straightforward change if you've been using it in the past. And if not, then you can use it in the future just as is. Then the next quick update, I guess there's two, is one in discretize. Dieter's also done some work. He's been busy making matplotlib a soft dependency, which is kind of nice. So if you want to install discretize on a server somewhere and you're not planning on doing any plotting, then we don't actually need to install matplotlib, which sort of lightens the software dependencies a little bit. And so that'll be coming in hopefully in the next couple of days. And then the third one is Devin's been working very hard on the documentation, and there's just like a few more things to polish off with the tutorials. And again, we should be able to get those in by the end of the week, which is awesome. So with that, if there's any other quick updates, feel free to chime in.
I think they're all thesis writing, so it's kind of boring out here.
I started that pull request for the MT stuff there. It's just little minor things, so yeah, I don't expect to to put that at the top of the list quite yet, but it's I started it.
Excellent.
Mike and I worked with the frequency domain code. So Mike is inverting galvanic source frequency domain EM data. with Octree code.
Nice.
Yeah, so I think there were some bugs for the kind of like there were quite a few like efficiency issues, so we had to kind of fix some. But I'm pretty sure we fixed it, and Mike is actually running his like EMN version. So yeah, he may update later.
So far, so good. So I'll let you know if I get anything good looking.
Oh, Mike was there. Great.
Excellent. Is there a way that you guys can bring those changes in, like in a somewhat small pull request? I realize that you've been working off of some branch, but are there like bite-sized things that you can bring in? Because we can do that quickly. If it's on a giant branch, it's going to just happen slower. That's sort of the nature of things.
Yeah, I think the change is actually pretty minor. So,
Yeah.
Mike, why don't you kind of make a pull request?
Okay.
Excellent. That'd be awesome.
Now that you're all here, Suggy and Mike, before I leave back to Belgium in July, I would like to get a bit more into the EM part also, not only the C. So how about you, Suggy? Are you available in July, or you're on holiday, or can I ping you sometime if I have questions, just to have a little bit of planning? Because in the holidays it's a bit less clear who will be there.
I'm available, but I think I will be in IUGG Montreal.
Okay.
So, but I'm still available. Like if you need some help, I can help.
Okay. It's mainly just getting me started, and then the rest will probably be fluent.
Yep.
Okay.
Perfect. Anything else?
John, did you have a chance to check with the Seabridge guys?
I sent off an email, but I haven't heard anything back. So it's that game again, waiting.
Okay. Sorry. So we inverted the DSIP data a long time ago, and then recently got a drill holes. So yeah, we were comparing, and then like a first order, it seems like matching pretty well with the gold assay, but we're not 100% sure yet. So yeah, we're in the process of confirming it. So yeah, we'll update you guys later. Yeah, we're not sure at the moment.
Yeah, I'll fire off another email tonight. Just keep bugging them. Power email them and see what happens.
Cool. Okay. Well, if that's it.
I was going to say there's maybe one more thing about documentation, but I can sort of tack it on to the end of the discretized stuff whenever you guys want to go over that.
Okay. Sure. Then let's turn the floor over to Sarah.
Okay, thank you. So I just wanted to share a bit with you what are the first results of the research here, and to get some feedback on what I did with SimPEG. So maybe to get you started, I wanted to show this, because that's actually, like with the internet quality, it will not be working so well. But this is what we are looking at actually in my research. It's an irrigated field, potatoes, and you see the sprinkler going there. So like the main questions that are present here are about how much water should we use? Are we irrigating in an efficient way in this kind of systems? And if not, how can we change that? Not only for the amount of water, but also in terms of leaching of solutes like nitrates. In Belgium, we are like, they call it a protect or an area where we have an enlarged or an increased risk of nitrate leaching. And so farmers have to be really careful about putting too much water and too much nutrients on their fields. So this is the context, and you can already see that such an irrigation is quite heterogeneous also. If you see like this huge spread of the beam actually due to wind, and also the fact that I just displaced this thing in the field until it's entirely covered. So we're talking about irrigation which takes like 2 days to do one irrigation of the field. So it's quite labor intensive, and it's because farmers in Belgium don't have to irrigate in a systematic way. They do it when it becomes too dry, and then I have some kind of a backup plan. So, so that's the question, let's say, of the data that I've been analyzing here is how can we irrigate potato fields in an efficient way? Or is it happening efficient at this moment? And how can we quantify this? Because that's the big question. You can see already we have this typical system with ridges and furrows. I don't know whether it's cultivated in the same way here. Yeah. Which makes it already quite complex from a hydrological perspective. Yeah, where does the water go that you actually apply on the system? There's slopes, there's accumulation, there's the canopy that gets some of the water, which can go to the stem then. So yeah, how can we quantify this? And in addition to that, here you can see how that looks from the inside. So typically, most of the roots are situated in these ridges. And there's some fine roots that go below, but most of the water and the nutrients are taken up really in this small area that is above the ground. And there's also these potatoes, of course, that are growing there. They're not taking up water, but they're also present and changing the environment, of course. And by the end, they get quite large as compared to the microtopography. So there is, of course, already some quite old research, even in this respect, you can imagine, because it's an old technique. So people have used different techniques to look at these things, like, for example, dye tracing. I don't know whether you've already seen studies like that. They use these food stain colors like brilliant blue or others and they apply them with irrigation water, and then they look at what's the pattern of this blue color in the soil afterwards by digging a big trench. Basically, it's very simple. And or you can put sensors at different locations in a trench and then see what happens after irrigation. That's another study with TDR. But the problem is in the literature, all these studies give very different results. Some say there's infiltration mainly happens in these furrows, and so a lot of it is lost because it directly goes to the groundwater. Others have shown, for example, with this dye tracing that there is interception of this water and it is efficient. So there's quite a controversy and not really a lot of quantitative information on what's really happening there. And why is that? Well, that's what I explained. It's actually a quite difficult hydrological problem. It's mainly the boundary condition which is not clear here. So if you look at the hydrological simulation, it's a bit like the electrical simulation. We have Darcy's equation, Richard's equation, and we have to set the top boundary condition, which is the rainfall. But as we know, in this system, it's not like there's one blue line which is homogeneous. We can expect that there's a different amount of water that is arriving on the top than on the sides and in the middle. And you can even see it more complex if you look at the bottom corner there. There is most probably, and that's already quantified, actually the leaves that are capturing a lot of water and directing it to the stem of the plant. And there could be punctually a very big amount of water arriving at some irrigation intensity. So that's also a difference. If it's like just a small rain, the distribution will be different than when you really have a big jet of water arriving in a short time. And then. So that's a bit the problem. And I think, or that was basically our idea, I think ERT could be a quite nice technique to show in 2D what's happening there. Like you can easily put electrodes on the surface. You could do monitoring, so leave the thing in place and then see where, when the water arrives after an irrigation event, where is the conductivity increasing, because that's mainly related then to the increase in soil moisture in this case. And yeah, so that's why what we did. So let's hope that with ERT we can find or at least make a qualitative picture of where things are moving and to which extent. And maybe also quantitatively, because we also have petrophysics, of course, and we could then convert it into real soil moisture. So that's even better, not only just an image of conductivity changes, but really go to soil moisture would be the ideal case.
If there's more water, do you expect the water to come out as conductive or
conductive? Yeah, conductive. But, and I'll come to that later, there's a lot of let's say complications in this, because often like farmers use groundwater for irrigation, so it's quite cold as compared to soil in summer. So you have like conflicting changes of or impacts on resistivity, which are less simple than it may seem. But in general, in an agricultural context, when water is added to the soil, there's immediately a lot of solutes which are dissolved or transported, and so water is generally more conductive or adding conductivity to the medium.
So in this one up here, you've got that trench in which there's been a fair bit of water.
Yeah, so this is actually the data you'll see at the end. So this is what happens after irrigation, actually. But so what's the point before doing that? So it has been done already, like in my group, we did it on several cases in eco-hydrological contexts, in forests, in mixed farming, but mainly on flat surfaces or on slopes, but without an important microtopography like this. And so how reliable will our measurement be in this context? That's actually the question that I've been asking myself here, or also when we set up the experiment is, okay, we have this small electrode spacing because we want to image very small scale processes, but we have a strong microtopography, which is really, it's as if you're measuring on a mountain with large scale ERT. And you were small scale electrodes, but also microtopography, which is in the same order of magnitude. We have the problem of, we are doing monitoring and we rely on the fact that, okay, we might even have artifacts on absolute measurement, but by making the differences, we really should be able to see processes. But adding the water is not the only thing that's happening. There's also erosion typically in these things. Like you can imagine that these bumps in the beginning, they're nice and smooth when the machine makes them, but then there's rain, wind. So this microtopography will degrade over time. And so how does that affect your measurement? Because you're not always aware of how this is changing. So
is that picture indicative of soil and then clay or something?
This is the podzol. This is a sandy soil with an accumulation of organic material in the top. Yeah, this is the soil we are measuring.
So
it's a typical
podzol. Quite an abrupt change.
Yeah, because it's a human-made soil actually. So what farmers do in this region, because it's a very poor soil, is that over hundreds of years they've added manure and organic material from the forests on top of their fields.
Oh.
And this makes such a soil. That together with some kind of humification process that is taking place in these real natural soils there too.
So initially it was just the stuff at the bottom, and then they just kept
if we simplify the story,
made the soil. That's
but you can see it like that a bit. Yeah.
It's starving farmers to like healthy farmers.
But you just hope it's not going to erode now. Right?
So what you have typically there in the landscape is this kind of beds, which curvatures. You really see actually that in the landscape that they've done this. But there's also a natural soil which is a bit similar in terms of accumulation. But yeah, anyway. And then the last thing that I was last thought that I have before we started is, okay, there's also these distinct patterns that are quite different that we want to recognize. We want to be able to measure an infiltration front, which is a homogeneous line going down through your profile, something horizontal, whereas root water uptake is something very local and a bulk, which is a very different pattern to distinguish. So we have to be sure that the array that we use is also sensitive to both kind of structures and not trying to deform one or the other. So yeah, that's a bit the context. And so what we did is like a study in two worlds. Like we started with a virtual experiment, as you guys often do. So I wanted to use actually forward modeling to have a better idea of this erosion problem. So which kind of artifact do we have to expect when we have a wrong estimation of this erosion, of the extent of the erosion? So here you can just see a loop of forward like simulation of the hydrological situation. We generate some typical patterns. We convert them from soil moisture to conductivity with a petrophysical relationship. And then we do the typical loop, forward modeling, inverse modeling, and comparing the real model and the inverted model. So that's for the question of the artifacts. And then we had a field experiment where we really wanted to look mainly qualitatively, because for the petrophysics, we still have a lot of work to do. Whether we can monitor these infiltration patterns, is that actually something feasible in reality, and what do these patterns look like? So that's the same kind of story, but there we have real data. So we start at that side, we do an inversion, and then we should get some qualitative information at least on the distribution of soil moisture. So that's what I did here. I started out with a virtual experiment, so I used a lot of DOMS knowledge on Octree how to generate a very beautiful mesh. I think it's almost something I would put at my wall. Huh? So you see this typical bumps here. The triangles are the electrode locations. And as you can see here, we're really small scale. So if you would project the electrodes on the x-axis, you would have a distance of around 6.6 centimeters between them. Give you an idea. It's a bit wider on the top to because the plant is there. So we did not put electrodes in the middle of the stem of a plant, of course. Yeah, we are using 1R alpha and dipole, quadrupoles, around 1,300 measurements, which should be divided by 2 actually here. So here it's because these are the amount of normal reciprocal, but in this synthetic world, we only had the normal measurements, of course. Yeah, octree mesh, the smallest cell is 2 centimeters, and then the inversion strategy was mainly the things I could find in the example. So that's probably something we could discuss today if you have some hints or tips to improve still the results. So simple regularization, inexact Gauss-Newton, updated sensitivity weights, and a target misfit. And as a reference model, I just used the median of the apparent resistivity. Because I think I didn't want to force the model towards what we know already in terms of layering, because in reality we don't know anything. So I just put a homogeneous background in the reference model.
So why did you find the mesh at just below 0.4?
For the transition between the 2 horizons. So that's maybe a bit of a, it's true that this is also something we probably wouldn't know in reality because we don't know exactly where the second horizon would be. But we know that hydrologically there's always a lot going on boundaries between 2 soil horizons. And also,
do you think the conductivity would be changing?
Yeah, of course. It is. That's what you also.
So it's really that tan layer that you saw underneath.
Yeah.
That's really conductive.
It's more conductive because it has more organic matter. So there's more charges in that layer. Yeah.
I thought the organic matter was the dark
The
layer
dark
on
layer.
top.
So that
and
that
then
layer,
underneath.
Yeah.
Okay, where you had the brown. Or
that's
the
less
tan.
conductive. Yeah.
That's less.
Yeah.
But is that where you start to make your mesh really?
Yeah,
fine?
that's there. So it's around that I refined the mesh to just be sure that I covered the transition between the 2 horizons.
But if you're going from a conductive to a
Yes.
more resistive
That doesn't
horizon,
make much
you
sense.
wouldn't ordinarily, I don't think,
No.
fine up the mesh. But
No, but it's something I could
Just-
change. I'm happy to hear these things. I just did it also, to be sure that we cover any strange things happening there. But might be good idea to at least try without refining it to see whether, because it artificially increases the sensitivity to a bit there, of course, if you have these finer cells. So it's one of the things I could look at. Yeah. Thank you. Yeah.
just something that kind of stuck out. That's really important.
Yeah.
Okay.
So then to look at the results, I think I just took out the most extreme erosion, like we take off 6 centimeters of the height, and the normal case. So what we did is we forward simulated all cases with the correct microtopography. So that's what you see in the first column. Like there would be an irrigation event, so is infiltration with 20 centimeters, one with ridges of 14 centimeters height only. So that's the real model on the left. And then the next column is we invert that with the correct microtopography. So what do we get then? You see already that it's hard to reproduce this transition between the horizons, for example. And then in the last column, we see the image where I ignore the fact that there has been erosion. So I invert as if my electrodes are still in the same place. As if I don't know that there has been any erosion. So I keep my initial microtopography and I invert the data of the eroded microtopography. Then you can see that, there's some artifacts that are being produced, that mainly everything is changed in the most sensitive parts of the ERT array, of course, which is close to the surface and in the ridges. And I do the same for the second scenario where there was rotator uptake, so a different type of pattern. And there, you can see the same effect, but it's even more strongly there because, you see it's mainly concentrating everything in the ridges at that point. So this is the most extreme case. It's probably never that bad in the field, but I just wanted to highlight, to which kind of artifacts you can come.
Sarah, are you using 3D model the data?
No, this is the 2.5.
Okay.
I could actually do that, but the point is I don't have a lot of information about constraining that dimension. So I think in this case, it's not very useful. When we would do transversal transects, like on the ridge, of course, it's necessary to go to 3D. Okay. So just to give you an idea of the difference between, if we start using this wrong microtopography, we get much higher data misfits, of course, too. So that's maybe like something also to take with as a take-home message. Okay, we have some artifact, but it's also visible, of course. You do see that the data misfit becomes much higher.
Like it plateaued, or?
Well, you see, like if you, this would be the same. If you have the correct microtopography, you get the data misfit of 3.3 here. And if I use the wrong microtopography, I have 800.
Yeah, but I mean,
This is for your first inversion, like the first iteration.
No, the last, the converged. Yeah.
yeah, but I mean, like if you were doing more iteration, will it still reach the?
But that's already 20 iterations or something like that. So I don't think it would add much more. I should have a look whether it's really plateauing. That's what you mean.
Exactly. Like, it's still
I can check that.
Or is that really plateauing? Like,
I can open the file later just to have a look at it. So you would maybe see if that's not the case, you would continue try to do more inversions. Yeah.
And
I guess, yeah.
What are your residuals? What kind of percentages did you put? What are your residuals?
All the rest is the same. So I put the same data error, the same. So I changed only the.
How are you weighting your different dipole spacing?
How am I weighting my different dipole spacing? Because the electrodes stay in place. Huh?
No, but usually, like, let's say your voltage is going to be higher.
Yes.
On the shorter spacings, right?
Yes.
Right. So how are you weighting your data uncertainties based on? Are you weighting based on those on the potentials?
Yeah, I just have like a relative component of I think 5% error on that. Yeah.
Okay.
But there's no difference between how I did that for the one with the wrong microtopography or the right.
No, but that might change the way your solution, right? That will change.
Yeah. Okay. Yeah.
Results.
Yeah.
Just look at your residuals. Make sure that you're not only fitting like the near dipoles.
Well, that's happening. If you look at the values, they are around what I would expect. But if I use the right microtopography, the data misfit plus the error are the values that I would expect normally. That's arriving at the right spot actually.
Did you have an error floor as well?
I tried some. I don't know whether this case was with the floor or not. I think so. Yes. Because for the synthetic, you have to put one anyway. Yeah, I think so. Sorry.
I've got a couple of questions. First of all, could you just roll back one slide?
Yeah.
So forget about comparison, with the topography or without. What's your assessment of the inversion with correct topography? Are you pretty happy with it? Is that informative to you, or where are you with that?
What I don't like, but I think that's the problem, is that the sensitivity of the array is very superficial. So the problem, for me, it's a problem that the horizons are disappearing. Because you could start interpreting these as, for example, drying bulbs or something like that, or wetting bulbs instead of, it's just the value of the horizon actually that you see there. So you get strange structures.
Do we have a laser?
Or use them?
Yeah, I can use them.
Yeah,
so what I mean here,
point out the things that you don't like, or the things
like
that
if you
do
see
like.
this here, this is the model, and here you have these green bulbs which are remaining actually from these background values of the horizon. You see? So this seems like something which has to do with the ridge, but actually is just related to the value of this horizon. But it's disappearing because the inversion is tearing the resistive values of the ridges down. You see what I mean?
Yeah, I just wanted to get a sense of what features you see on the inversion were actually like, oh, I'm glad I got that. That's pretty informative. Or which ones were like, well, that's really a bad artifact, and I want to get rid of it.
But what is good, for example, is that we seem to capture these infiltration fronts quite nicely. And the thing that I don't like is indeed that but that's probably the array. It's not the inversion. It's the array which is not capturing, not going deep enough to really be sensitive to both horizons. So these horizons, these things are very dependent on the background and reference model that I use.
And what is it?
Well, I'm now trying several, so to see really what's the impact until where it reaches. But you see that if you use one which is close to the values on top, it's smearing everything out to the bottom. And if you use one which is further away from that, it's not doing that. So it can have quite an impact actually from half a meter downwards.
So
Where
you also think about thinking about the experiment as a time lapse, right? Because
that's
then
true.
you've got artifacts that are coming in,
They're
your
disappearing.
baseline inversion, and you're only interested in where the water is going, what the water is doing.
Yeah. So that's exactly why I'm not too worried about this. So maybe I'll continue because otherwise I'll take too much time.
Okay.
But here,
one quick question.
Yeah.
Okay. Would you typically have a good estimate of where that conductivity contrast is happening between sort of those two layers, between the top more conductive layer and the lower resistive, or sorry, other way.
sorry, I didn't understand the first part. Can you repeat?
Could you have a reference model that has both the bottom layer and the top layer, basically?
Or do you actually typically know where that interface is, or have a good estimate?
Most of the time you have an idea, but yeah, it's not horizontal plane thing, but you can make an augering and have an idea where that is. So a lot of people use that in inversion. They'll set like a 2-layer reference model, but you also force it then to follow that. So yeah.
Is your array sensitive to that the depth of the
yeah, I guess so. Yeah.
You're supposed to.
Well, I did also some trials with that, and then you get it much nicer, of course, because yeah.
But you are sensitive to it. Like your
Well,
dipole spacing is long enough to be able to reach that.
No, you're a bit, yeah, it's more or less up till 0.6 that you get sensitivity, and then the rest is much less. Yeah. But, and that's here just the same, but if you do it in a 1D over the ridges and the profiles, it's just to show that the stars are actually the ones which are inverted with wrong microtopography, and then you see that mainly it deviates at the surface always, just the same message. We are actually creating artifacts very close to the surface with this kind of problem. Okay, so that's the 1D. Then let's go to the real experiment. So I did exactly the same there, apart from the fact that we also have normal reciprocal measurements here. So we have an idea of the error, and we have a time-lapse experiment. So we have like about 9 measurements over a few days, to get some idea of how things are changing over time. And we have some sensors also in there. The stars in this drawing are sensors, soil moisture sensors and temperature sensors to get to the petrophysics actually. To give you an idea, what we did here is, this is the climates before, and you can see that starting in the end of, in the end of May, we didn't have any rain anymore, so it was a very dry season. And then these green bars are the irrigation, so the farm had to irrigate a lot this year. And what we measured is one of these events. So you see here, this one, we had even more than 3 ERT measurements. I have to update this figure. So you'll see what happens after that one irrigation. And the lines you see there are soil moisture sensors. Basically, these sensors show that we had a big response in the furrows and that we had almost no response in the ridges. But that's only one ridge and one furrow, of course, with the sensors. So this is the ERT inversion. I tried with different error levels and with different settings, and again, you strongly have this smearing downwards of the structures in the top. So I don't know, is there something else that I could try there? But let's discuss that later, because it's indeed always important to look at this time-lapse result, and that's what you see here. So here you see basically the difference between the first inversion and then every time step divided by the first one to have a relative change. So you can see that where the water is coming in these furrows, that we really are talking about big changes. It's more than 15 times the initial conductivity. So that's the blue values. And this way you can, it's not so visible here, so I should probably use another color scale. Yeah, we do see now that there is mainly infiltration in the furrows. If we make this difference, there is no artifacts popping up one time and then disappearing again. That's also nice to see. So that means that if we have artifacts through the inversion, they are constant over time, and so they're not like disturbing our process understanding. And we do see that, for example, here in the beginning, we also have some ridges where water is arriving. It's not only in the furrows. So we probably have a mix between the processes that I've been describing in the beginning. Well, anyway, so qualitatively, that's what we see. We have this strong connectivity increases, then it gradually decreases over time, which is also logical. What is also nice is that we don't seem to have this kind of drainage towards the bottom of the profile. So it does stay, like there's a strong increase, but it's not going through entirely. So it might be that there is ponding or like a big increase of water, but that then it gradually dissipates towards the rest of the profile through capillary force. And then the ridges too, that you have something there. So yeah, for me, conclusions at this point are that we can, with time-lapse ERT, still reveal some patterns that are relevant to the process that I want to study, even though some of the things with inversion are still quite tricky. So the conclusion that I just made, that these furrows mainly, range seems to be limited. But then there's one thing that I still wanted to say here, because that will be the next thing for me, is connectivity is of course not equal to soil moisture. We have a non-linear relationship between both. So to really look at patterns, I should compare to soil moisture, because some connectivity changes will not be very relevant in terms of soil moisture and others will be. There's the impact of these huge potatoes also, because they grow. Of course, over a few days, that's not really problematic. Again, in the time lapse, the potatoes will not grow in 3 days until. But if you study an entire growing season, then I'm sure that this will impact also the conductivity, and then you have to have some idea on how to change your petrophysics, of course, for this kind of living system. And temperature, I'm pretty sure that, yeah, sorry?
So this is probably a naive question. Are potatoes a conductor or resistor relative to the?
Well, I have an entire project at the moment, which is called E-route on the electrical signature of plants. And it's not an easy answer. I would think with the potato, depends on the type of measurements you're doing. But with ERT, it's probably not necessarily acting as a conductor, because the cells are protected by the cell wall, and you're not going to get easy current through. But if you would put current on the plant, for example, and measure in the soil, you might have a very big conductor, because then you get like certain vessels that are. So it's quite complicated to answer to that question.
Fair enough, fair enough.
But worth studying, probably, yeah. And yeah, the temperatures for me, an easy one probably we should have a look at. We often just use a temperature dissipation model in soil to at least get an idea of, okay, what could be the impact? Because the water was in summer really 10 degrees colder than the soil actually. So that could start having an impact on the petrophysics, of course, if we want to get to soil moisture. So questions I have for you. Yeah, sorry?
The end product here, like, so what's actually important at the end of the day is a soil moisture?
Yeah, for me, that would be the ideal case, that we can really get, well, the changes in soil moisture. The absolute value is not important, but the changes.
Right. And then why that's important? Like, how would you use that at the end of the day?
Because then we can estimate things like water use efficiency. We can calibrate fluxes, water fluxes with a hydrological model and things like that. Yeah.
Right. Gotcha.
So as long as you have a good before inversion, then good.
Yeah.
It doesn't really matter what the.
And that's why the soil moisture sensors are important. Then you can, if you have the changes, you can just use them to calibrate. Yeah. 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 So questions I have for you is mainly, yeah, I'm still working on this impact of the reference model, stuff like that. So looking at that sensitivity and how different background models are, yeah, affecting this sensitivity distribution. But then questions I had to you mainly was, are there things you see in the inversions now that are obvious problems that I'm not taking, like, are there easy measures to implement that I haven't tried yet maybe, and you see, maybe you should try that? And another thing is, do you have an idea how to link what I have in this first part, the synthetic part on the artifacts with my, can I use some of the information we got from there to do a quality check on my data of the real experiment? Like, how can we link somehow this knowledge that we have on typical artifacts to expect? Like, I don't know, quantitatively, how can we do that? And I have like an idea where they appear visually, but I would like to use both together in one story, really, like to show, okay, we get knowledge here. I want to take that into account when I'm evaluating my real inversions. So if you have some ideas for that, I'm also curious.
Sarah, can you elaborate a little bit more on the last item? I wasn't sure.
The last item, like the link between the synthetic and the real example?
Yes.
Yeah. So for me, I now have like this visualization, spatially, of artifacts that I can expect when I have a wrong microtopography estimate. And I have an inversion of a real case where I only have the initial microtopography. So would there be a way to connect like the knowledge we have on artifacts to expect to like, I don't know, analyze the patterns that I have in the real image? Maybe I'm looking too far.
No, that's good.
Yeah.
You're hoping to be able to learn something from your poor inversion in the synthetic to be able to improve your real life. That makes total sense.
But maybe there's some steps missing to do that.
You're looking to like automate it, not just be able to visually pick it out by and say.
Not subjectively, okay, that looks like the same type of artifact, but is there some way to just
quantify it?
Run some spatial algorithm on it and say, okay, that looks too similar.
When you do the repeat measurements, you use like the same electrodes?
Everything stays in place.
Everything stays in place. Okay.
Yeah.
In your synthetic example, were you taking into account the lengths of the electrodes? Because I think at one point you had mentioned that they were actually pretty deep.
Well, they're 13 centimeters deep. And so what we do now, I'm not modeling the electrode, and which would be another, I cannot do that in this paper, let's say, but it would be something to study, is that now I'm using a point electrode, which is at 60% of the buried length of the electrode. So that's what you see there in that drawing. And if it's eroding, I'm taking into account the soil is leaving to change that point. Like imagine you have 10 centimeters electrodes in the soil first, and then it's starting to erode and 2 centimeter leaves. Then I put the point at 60 centimeters of 60% of the remaining buried length. That's what you see there with these dots. So if they're buried more, nothing happens, but if soil is removed, then this dot changes a bit.
But so in each furrow, which is only like 20, well, there's like 40 centimeters wide, right, from trough to trough? And then you've got like 4, so every 10, you've got electrodes sort of every 5 to 10 centimeters.
Yeah.
And then you talked about different arrays, something Wenner alpha and something. What exactly are those?
Which measurements I did exactly? I should look at so the dipole is just like, probably that's people don't see me, but this one. And the Wenner alpha, isn't it the one, I have to, I think it's the measurement inside and the injection outside.
Yeah, that's. Is there any difference between what we call a Wenner and then a Wenner alpha?
Yeah, there's a small difference in the spacing.
Actually, this is the transmitter, it's the receiver. The distance is.
Yeah, the Wenner alpha is the same, but there's a difference between the A and the B's a bit. Like how large the two dipoles are, but I can't tell you.
Oh, okay.
But that actually comes from a study that a master's student did. He did a lot of different arrays before he did the thing with the erosion. He tested on this microtopography different types of arrays, and this combination gave the best coverage and best sensitivity for the processes that we want to measure. So it's even, he tested more than just these two.
So if you're to think ahead and try to put this into kind of like a production level in a field, what do you envision for like the number of electrodes that you'd be wanting to use, and how would you scale this up?
So for a farmer, this is not feasible. I mean, for an experiment, you could scale this up, but you need this resolution, because I think already our resolution is limited because of the fact that you have these furrows and ridges and you can't put electrodes anywhere. But if you want to see changes in soil moisture at roots, linked to root water uptake, you have to have this resolution. So, but for me, that's not something a farmer would do. Like, that's why we scale up in this project. We have these EMI measurements. So it's much easier to walk in a field with an EMI device several times, and then if you can link that to the process knowledge we get from some ERT and more like scientific experiments, I think that's much more useful.
Okay, so your goal here is to kind of do a two-step procedure. One, with ERT, and just try to micro look to see what you can really tell with respect to soil moisture and irrigation. And then once you know something about that, then you could use an EMI, something that's really transportable, go across the fields, collect information about the conductivity.
Because that's realistic for a farm.
Okay, okay, no, that actually sounds good, because I was kind of worried about.
No.
Wires.
No, this is just like, this is more for our understanding than something else.
That's good.
Yeah. So I don't want to take too much of your time, so tell me if I...
Just one more question. When you're doing your synthetic, did you actually add noise?
Yeah, I added, I think, 5% noise. Should look up Gaussian noise and like scaled with the resistance. Like a relative component. So the noise, it's a relative noise with the...
Right, so you took your voltages.
Yeah.
And you just added 5% and maybe a floor too, or not?
A very small floor, but that's just for modeling.
Okay. And then you use the same percentage and floor when you when you did the inversion. Yeah. And then the numbers that you were getting out, I forgot. You actually had a lot of decimal points, which we usually don't bother with.
Yeah, that's true. I just copy pasted from the file actually.
Yeah, so 320. So is that about the number of data that you have?
Well, I had 360 data points.
Oh, okay.
Sorry, no. It's 670, so that should come to around 360 because we have to divide by 2.
Oh.
Are
we ever going to get on that? Okay. So this is a half phi d.
Yeah.
Or phi d's. Okay.
I think I would still because your bottom resistor is going to be in your very, very weak potentials, right? There's not much going to response current there. So you want to make sure that you're fitting your background long offsets.
Yes.
And so make sure that you plot your pseudo sections or you plot your data, and that you're not overweighting those like small potentials. You obviously don't want to weight the.
So maybe put the floor higher then, or what, the cutoff higher?
For each dipole spacing, have a floor, its own floor for each dipole spacing.
I'll discuss it with you later.
It's like doing a barren resistivity covered back to voltages, and then use each for those. So that way you, because you don't want to fit only the near surface. You want to fit the bottom too, right? Yeah, we met a suggestion. Okay.
So if you'd have any suggestions for me later on, you can always just send them to me by email.
And side question for you, are we ready to do parametric conversion for the reference model? That would be perfect for that, right?
Yeah.
To just invert for the interface?
Yeah. So,
Should you do a best fitting? Go for it, sorry.
Yeah, I showed you an example. So, you do like a polynomial voxel, or like just like some sort of interface plus voxel. Yeah, I can maybe show you next week. You guys next week, or send you a script. Just script Sarah if you want.
Because then it's a two-step process where you invert both the interface and then for the whatever anomalous water infiltration. But you want to make sure you nail your reference model well, because that's going to influence you.
Yeah. Okay. Interesting. Yeah.
Excellent. And would you mind sharing your slides or just posting a link to them in the meeting notes? Would that be all right?
No problem. Yep.
Thanks. That'd be awesome. Any other questions for Sarah? No? If not, the last item that I wanted to chat about briefly was the simulation pull request. It's still very much a work in progress. But I've left some questions and things in there that I would really appreciate input on, because this, like, what we're looking at doing is refactoring like the problem in the survey. So we'll no longer have a problem class at all. We'll just have a simulation. And the simulation takes a survey and a mesh, and it has at a bare minimum, it would need to have a dpred, a jvec, and a jtvec, and that's it. And so that'll let us actually plug in other codes much more easily. So something like EMPyMod, for example, all we have out of there is a dpred, and then we can estimate jvec and jtvec just by doing finite differencing. And so then we should be able to immediately plug that in and invert. And I think this will also get rid of the naming complications that we've had with just referring to problem throughout SimPEG. And so as I've been doing this, been looking at renaming some things, because like this is a non-backwards compatible change. And so it's like we're already going to have to update a number of things. And so in this case, might as well just like go and update lots of things, I guess. Trying to make it like as backwards compatible as possible. Oh, are people still there? I've lost video for everyone. Anyone still there?